So anyway, sorry, my voice is really kind of goofed up. I feel just fine, but it might be a little painful to listen to. So let's begin with questions. You did have not only a study assignment, but you had some exercises you were supposed to do. Difficulties? Sure. 49? Can you tell me? Oh, brother. What did I do? I have to get my board. So it was on page 462. Thanks. 49. Okay, sorry, 49. 3. Complement and supplement, and these are all what? What you probably didn't figure out is, what is that talking about? Radians or degrees? The only time it's degrees is when they have the little degree symbol. So 49a is saying 3. Okay, maybe that was a problem. But anyway, what's the complement and the supplement? Well, in radians, what do complements have to add up to? Pi over 2. So we'd have to subtract from pi over 2 to get the complement. So, and what would we have to subtract from to get the supplement? So, it's all, in degrees, we know that a plus b has to equal 90 for a complement. And in degrees, a plus b equals 180 for a supplement. In radians, it's a plus b equals pi over 2. And in radians, a supplement is a plus b equals pi radians. So that's the basis for doing 49, at least part A. Similar thing with part B. So all those numbers in 49 and 50, those are radians. So you probably looked in the back, and I'm going to guess you probably had 87 and 177 or something like that, and you probably thought, then that would be true if 3 was degrees. Matt, did you have a follow-up?
Yes. Well, say, for example, if you wanted to convert the radians into degrees and then calculations, you still have incorrect answers.
Oh, yeah, but that would not be a good way to do this. It's possible, yeah. He said, could you convert 3 radians into degrees and then do it in degrees and then translate it back into radians? Yeah, but it's a lot of extra horsing around. Should it come out the same? Yeah. See, the problem with converting is you're going to get a decimal. And in radians, we don't like to list radians in terms of a decimal. I don't like to say 3.14159 going on forever radians. I'd rather say pi radians. And so we like to have pi in our radian measures. And the problem with converting is your calculator would give you some kind of a decimal. Decimals aren't wrong, they're just not as handy. Another question?
Same thing here. I understand how to do it, but what is the like? Why do the complement and supplement show?
Well, for example, if we were in a right triangle, then what does that tell you about the two acute angles of a right triangle? They have to be complementary. See, that's a pretty handy thing to know how to do. So if you know one angle, you can find the complement to find the other one. Or when you have a straight line with a line coming down and dividing it, of course these two guys are supplementary, and that's again very handy to be able to do that. But those would be the big purposes. Other questions? I'm done. I don't want decimals. You could go ahead and get a decimal, but they're just not as useful. So my guess is, sorry, if you look in the back of the book, I'm thinking you should be seeing answers like this. And did anybody look? That's not what's back there.
Pi minus 3 is converted to 124.
What?
There's that most pi minus 3 is converted to 124.
Oh, so they put both down.
That's what,
And on this one, do they have it like this, congruent to something else? Yeah. Okay, so they put both down. Honestly, this is what we want to see. We don't want to see the decimal. So this is actually done. Now, here, but another comment, something that's kind of deceiving in this particular problem, Kevin, and that is, very rarely do you see bare radians like they have in that problem. By bare radians, I mean like 3 radians. Most of the time you're going to see 3 pi over 2, or you're going to see something with a pi in it, usually. There are going to be a few times, in fact, we're going to have to learn how to handle, I guess you could say, call them naked radians. They'll come up a little bit. Probably should have warned you about that. There are going to be some naked radians in this course.
Yes. Yeah, they do have, like in 37B, they have like a negative 3. I don't understand.
37B?
Having pi in there, how do you figure that out?
Okay, that's probably, okay, let's see. 37B. What are we supposed to do there? Oh, sketch the angle. Okay. Well, the only thing you could do there is convert it to degrees. This is, because otherwise you're going to get, how big is a radian? By the way, a radian is about 57 degrees. Do you know how you can do that? Oh yeah, this is another little thing we should talk about. Calculators. I'm going to be doing almost everything without calculators in this part of the course. However, it's important that you know how to do a couple things. When you use sine, cosine, and tangent on your calculators, you've got to be aware whether you're in degree mode or radian mode, because the answers are totally different. And you're going to have to figure out each calculator is different. There's 2 modes, degree mode and radian mode. Anyway, how do you pick, what's 1 radian? 1 times pi over 180. 5 out. Did I do that right? No, just the opposite. 1 times 180 over 5. And you're going to, so go ahead, somebody on your calculator, do 180 divided by 5. And you should get 57 points something. Okay, there's your, that's what 1 radian is in degrees. It's not some nice magical number. Then you could just multiply that by 3. And now you could sketch your angle approximately. And what was it, a negative 3? So you'd start here and you'd go that many degrees and clockwise direction. Yeah. So that's probably how you'd have to do it. That's a little bit of an awkward problem. That's how you do it. Just so you know, yeah. I guess enough said. Other questions? I think there's a quiz. There is a quiz. Not very long. Yes. Yeah, let me just make one quick comment first. Probably the toughest question on there, in my opinion, is what is a radian? They're not easy to describe. I would put it something like this. The angle formed by two radii in such a way that the arc cut off on the circle is 1 radius in length. You don't have to use those words, but it's got to have something to do with that arc on the circle being 1 radius in length. And it's got to have something to do with length.
Can you say like the measurement length that now can be converted into an arc length? Or is
That's pretty good, actually. Arc length is good because it tells me that it's on the circle. That's pretty good. I want to see the whole thing, but I like a lot of that. Okay. It's time for Trig 3. Okay, on the outline, here's where we are. Yes. Yes. I guess maybe you should just ask, are there any more review questions before we go on? Things from before today. You can bring those up anytime. Okay? Today is a big day. They're all big. They're all big, but what's really big today is, I hinted at this last time, 2 special triangles from geometry. And these are going to be the basis for a lot of things in the next days coming up. The first special triangle is the isosceles right. The isosceles right. Now I'm telling you 2 things about that triangle. That it's a right triangle, and at the same time it is isosceles. So, using the picture on there, where does the right angle have to be? It has to be here. Which 2 sides are the ones that have to be equal? It's got to be the legs, right? Can a hypotenuse ever be equal to a length of a leg? No. So let me just mark. That one and that one have to be of equal length. Okay? And can you tell me about these 2 angles? See, Christina, here's where we're going to apply some of that stuff. Those 2 angles have to be complementary. Why? Geometry question. Right, the total has to be 180, and we know 90 had been used. That means we got 90 left for the other two. So the two acute angles of a right triangle have to always be complementary. So what does that make them if they're equal? Oh, by the way, are they equal? Yeah, there's another geometry theorem. If you have an isosceles triangle, don't you know that the base angles have to be congruent? So what do they have to be? They're really 45-degree angles, right? For the moment, we'll use the degree name. Okay. Okay. Now, based on last time, let's just say, yeah. What's the sine of 45 degrees? Okay. Now, memory work from last time. The sine is equal to the leg opposite divided by. Oh, we don't have any lengths here. Because these two are equal, I'm just going to call them both 1. Okay? They're equal. It could be any number, but I'm going to call them 1. It'll make it easier. Can you calculate what the hypotenuse is? Yeah, you would use the Pythagorean theorem. Let's quick do it. One leg squared plus the other leg squared equals the hypotenuse squared. And hopefully you can see that the hypotenuse has to be the square root of 2. So I'm going to mark it now on the diagram. Okay? All right. So what's more important is that's not the length, but that's what? The proper ratio. If the legs are 1, then the hypotenuse is the square root of 2. Now tell me, what's the sine of 45 degrees? Well, pick this one. I don't care. Sine is leg opposite over hypotenuse. And right away, I want to stop and make a comment here. I actually prefer this answer. Now, I know we kind of, conditioned you to not put answers with square roots in the denominator, but I actually prefer it that way because it shows me right on the position of the triangle what's what. So you do not have to rationalize this. Some books will write this as the square root of 2 over 2 because they'll multiply top and bottom by the square root of 2. I'd actually prefer that you just leave it like this, okay? I think it shows you the ratios better, okay? Now, somebody else tell me this one. Based on that picture, what's the cosine of 45 degrees? Yes, it is. Okay, you were using this angle again? If you use this angle, where's the leg adjacent? It's right down there. 1 over the hypotenuse square root of 2. What's the tangent of 45 degrees? 1 over 1, which is just 1. Okay, now this is the cool thing. Because of similar triangles, the sine of 45 degrees will always be 1 over the square root of 2. Forever and ever. Amen. And it just can't be anything else. And the tangent of 45 degrees is always 1. And so, again, it's all because of what? Those ratios forever hold true when you have similar triangles. Now, the only other thing I'd like to do on this page is I have committed a bit of sacrilege on this page, and I need to undo it, okay? I really shouldn't be using degrees, okay? I wanted you to think it through the first time because in geometry you thought of degrees. But really, the way this should be stated is first of all, is that correct? Is 45 degrees pi over 4? You guys are supposed to study that for the day. Okay. And the cosine of pi over 4. I guess I shouldn't say it's sacrilege. I'm going to use both degrees and radians. And I want you to get used to both. The thing is, you're already used to degrees, so. Okay. So, let me make a point here. You see how we just learned the sine, the cosine, and the tangent of an angle, and we used no calculator. We used the Pythagorean theorem, and we used some geometry. The geometry of isosceles triangles have to have equal base angles. Okay. Basically, I am going to be hammering away at how to do this stuff without a calculator. I'm not against the calculator, no way. It's just that I know what's required for calculus. I'm teaching it. I know what people have to know. You got to know how to do this without a calculator. Then you can go ahead and use a calculator to confirm things, you know. I'm not like I'm gonna, but just about everything I'm going to be doing in the next 7 class days, no calculator. Okay, so get used to going without. I mean, you can go ahead and check it. I mean, you do this on your calculator. If you're in degree mode, what's the sine of 45 degrees? It's about 0.707. Why? I just have that memorized. I think it's 0.707. Somebody check that? Yeah. And so is the cosine. And here's another one I have memorized in decimal form. The tangent of 45 is 1.0. Stayed up late working on that one. No, not really. Okay, next. This is the other special triangle. I just called it on top 30, 60, 90, named by its 3 angles. So obviously, this is the right angle. That's the 90. And the bigger one here, that's got to be the 60 degree. And this one is the 30, at least it's supposed to be, if I'd have drawn it. Now, here's the big geometry thing that you have to remember. In a right triangle, the side opposite the 30-degree angle is half the hypotenuse. In a right triangle, the side opposite the 30-degree angle is half the hypotenuse. Now, it doesn't have to be 1 and 2, but again, 1 is a nice, easy number to work with. I could have put 2 and 4, or 3.5 and 7, but can you find the remaining leg? Of course you can. Take a few minutes on your paper and calculate the missing leg. By the way, I just have to tell you, when I talk about a missing leg, I have to tell you a strange experience I had when I was growing up. My parents would take us camping. I went on a lot of camping trips. And one of my dad's friends, their family would come and camp with us. And the dad in this family had a wooden leg. Okay? And one night we were camping, and it was just horrid. I mean, we were in bed, and all I can say is the skies opened up. It rained so hard that things started floating away. Okay, and you know, you can hear of course all the mothers wake up first and they go, did you close the car windows? You know, all that kind of stuff, and they're doing the final checks. Do we have all the kids here? You know, one of them didn't go off to the outhouse and then float away or something. You know, and the wife, Fink is the guy with the wooden leg. His wife says to him, and you can hear, we're intense, okay? So everybody can hear everything. And Ginny, his wife, says, "Hey, would you get up and check the car windows, please, right now?" He's like, he's like, come on, I'm tired. Get out there. And there's all this rustling going on, and she says, why aren't you getting out there? And he says, I can't find my leg. And it had floated to another part of the tent. Okay, I'm sorry. So when I talk about a missing leg, my leg is missing for the moment, and all I can tell you is that was so funny sounding. We laughed so hard we had tears in our eyes. So we're in the middle of a storm. Everything's wrecked. The tents are leaking, and we are practically crying because we're laughing so hard. So anyway. Hey, what's the missing leg besides Sphinx? Square root of 3, right. Very good. And therefore, now I'm going to throw a little curve at you here. We've got two angles we know the trig function is for. We've got both a 30 and a 60. By the way, last time we had two also, but they were both the same. They were both 45s. So be careful. When I ask you for the sine of 30, what do I want? The leg opposite the 30 is down here, 1, over the hypotenuse, 2. Cosine of 30. Leg adjacent to 30, square root of 3, divided by 2. Tangent of 30. Leg opposite, 1, over leg adjacent. Really sorry about my voice. Okay, and then we also know what's the sine of 60. Now I got to look down here. Leg opposite is now over there, square root of 3 over 2. Cosine of 60 is the leg adjacent, 1 over 2, and the tangent of 60, leg opposite over leg adjacent. Okay, again, no calculators. So, what I'm trying to do is, and by the way, I have good news for you. These are the only two special triangles that are going to motivate us. So you have to get to know these triangles intimately. Okay? I mean, you got to be able to sit down and draw them and come up with these three numbers. 1, square root of 3, 2. In fact, a lot of the quizzes I will give, I encourage students to sit down and go ahead and draw those triangles right on the quiz, because they're really the key. Once you have the triangles, you should be able to read off everything else. That is, if you know SOHCAHTOA. I mean, if you know your definitions. So, top priority for next time. Know your triangles. There's two of them, the isosceles right and the 30, 60, 90. And then, I don't want to forget this. I mean, don't forget, for today, you were supposed to be able to do this too, right? So, see, here's where we're headed. Eventually, we're going to have charts like this, okay? And, I'm going to just say this is the degree row. Let's call this the radian row. And let's change colors here. I haven't really taught you 0 and 90 yet, but we just figured out from that triangle that the sine of 30 was 1/2, didn't we? And the sine of 45 was 1 over the square root of 2. And the cosine of 45 was 1 over the square root of 2. And the tangent of 45 was 1. And the sine of 60 is the square root of 3 over 2. The cosine of 30 is the square root of 3 over 2. The tangent of 30 is 1 over the square root of 3. And the tangent of 60 is the square root of 3. Check those. Those look correct based on what we just did. Also, you should be able to fill in this row. Translate these degrees into radians. Okay, 0 degrees. That's a tough one. Yeah, or 0. Yeah, I said it was tough because I meant 0, 0. But yeah, you can say 2 pi. 30 degrees, 45 degrees, 60 degrees, 90 degrees. So, this, I would say right now, this is the extent that you know this chart. Well, I mean, you will Monday. I haven't given you any chance to study it, but. Now, I haven't done the 0 or the 90 functions, but we'll get to that. In fact, maybe we'll begin that in just a few minutes. But I wanted to show you where this is heading, okay? Eventually, I'm going to add more and more angles here for different quadrants. Okay, this is going to go probably up to about here. I'm going to go past 360 degrees, but I'm going to stick with the special angles 30, 45, and 60. Where did I get those from? The 2 special triangles that I talked to you about today. And then I'm going to go down twice as deep. Eventually, we're going to go to all 6 trig functions. So this chart is going to get rather large, okay? But this is the core right here. And if you get this, you're probably going to get the rest of it. Now, this isn't hard, but this is really important. If you get this approach, I really tailored this toward what you need for calc, okay? So I guess let's start looking at, okay, now here's what I mean by a, actually that's pretty much the end of the material for today, but I'm going to just give you a peek at where we're going. What I call behavior charts. I'm going to teach you a behavior chart for sine, for cosine, and for tangent. Here's the one for sine. And let me explain a few things here. Actually, these are actually visual things. And in fact, yeah, I've got a little animation I think I can show you after we go a little further here. Okay, first of all, the sine, remember, this is a unit circle, right? So what's the length of the hypotenuse in my 2 right triangles that I've drawn there? You know, what I mean by them is, this part. The hypotenuse is 1, isn't it? If the circle has a radius of 1, then isn't the hypotenuse a radius? Okay, so when you do like leg opposite over hypotenuse, like adjacent over hypotenuse, the hypotenuse in this beautiful simplified version is 1. And what happens when you take something over 1? It stays the same. So, where's the leg opposite? If this is our angle right here, you know, here's theta. If that's theta, where's our leg opposite? Isn't it this guy right here? So if you watch that vertical leg and take that angle and rotate it around, and if you keep your eye on that blue leg, you actually will visually see the behavior of the sine function. Okay, now if you can picture that thing being totally collapsed at 0 degrees, how high will that blue leg be? How high will that blue leg be? 0, right? It'll be flattened out. And then as it goes up, the blue leg's going to get bigger, bigger, bigger. What happens when I get up to 90 degrees? Well, the triangle will have collapsed, but how high will we be? All the way to the top, which is 1. What does that tell you? It tells you the sine of 90 degrees is 1. Now what happens when I keep going? That blue leg will now be over here in the second quadrant, but it's still above, so it's positive. It's going to start getting smaller, right? And when I get to 180, 0 again. And what happens when I get in the third quadrant? It's going to go below, which means it's negative. And it's going to go all the way down at 270 degrees. It's going to go down to -1. And then it's going to start coming up. -1, less, 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 and it'll come back up to 0, and then it keeps repeating. So if you can picture that little animation, you're seeing the behavior chart. Okay, now, let me explain this. What I'm saying here is in the first quadrant, wouldn't you agree the blue leg is always going to be above the x-axis and therefore positive? Isn't it also increasing? As I do this, doesn't the blue leg get longer? So in the first quadrant, the sign is positive and it's increasing. Second quadrant, positive because it's above, but decreasing because as I do this, it's getting shorter and shorter. Third quadrant, it's below, so it's negative, and it's getting negatively larger, which means it's decreasing. Fourth quadrant, it's going from -1 back to 0. It's negative, but it's increasing because it's getting negatively shorter. Behavior chart. Let me find that animation, if I can. Can't remember what I named it. Here we go. Okay, now watch as I drag this. The green, in this case, they made it green, but do you see how the green gets longer, longer, longer? At 90 degrees, it's at its top height. And by the way, you can watch it in the top left corner. They've got the values there. The sign has gotten to its top value of 1. As I keep going, do you see how the sign is now decreasing? But it's still positive because it's above the x-axis. At 180 degrees, the sign has shrunk back to nothing. Now, because we're going below the x-axis, notice we, for the first time, have a negative SINE. By the way, I'm not insulting your intelligence when I start spelling things out in this. You'll hear me say, what's the SIGN of the SINE? And the reason I do that is because otherwise it sounds like, what's the sign of the sign? And you're like, huh? And unfortunately, they're homonyms. And I need you to know which one I'm talking about. So anyway, do you see how the SIGN of the SINE is negative? And it's getting bigger, negatively. Goes all the way down to -1. And now it starts getting negatively smaller, which means it's increasing. Shorter, negative. Finally back to 0, and off we go to the races again. And we do more of the same. That kind of an animation, honestly, is what I'd like you to have going on up in your projector up here. And if you learn the 2 basic triangles from today, and if I haven't shown them to you, but when I show you all 3 behavior charts, if you can get those, wow, you got it. So that's kind of where I'm headed. Now, let me go back to the outline. Now, we're going to give you a little assignment on 6-2. And that's all we'll have before we leave here. Now, remember what I told you about how I like the sine of 45 to be 1 over the square root of 2? This book does the rationalizations of denominator. So they will say the sine of 45 is the square root of 2 over 2. Well, it's the same thing if you rationalize 1 over the square root of 2. Anyway, just so you know, the book, well, if you look on page 467, you'll see they have a little different format than we do. So let me get an assignment here, page 472. One to 25, the odds. Let me write it up here. But more important, study. Where it is, there might be quiz. Shot. See, now there's one good thing about the many quizzes. I'll say there's going to be a quiz and I won't have all these typical trends. Other classes have a quiz. And right away they need, the emergency EM people to come shock them. Happy Thanksgiving, everybody.
I don't get the whole angular radial. That confuses me.
Oh, are you guys doing angular velocity?
No, we're doing stuff like
Electron rotation or something?
orbital, yeah.
So, interesting, fairly close stuff.
Yeah.
Maybe.